have a big catalog of all of the things Alice might see, which she's still standing outside the computer perfectly comfortable.
Yes.
Outside the hole, versus like she'll want to still know if she's going to burn up if she jumps in or not.
I would say that if you're asking the question, I mean, there's a question of personal identity, I think, some philosophical question implicit in what you're saying. That which Alice is which? Is one of them the real Alice or one of them the virtual Alice? There is definitely a philosophical presumption that you're getting at in your question, which is that if you have a sufficiently high fidelity simulation of Alice's brain, a sufficiently high fidelity quantum simulation of everything that Alice can do, that is of equal dignity with the original Alice. That's, I think,
Clones of Alice or just classical simulations of Alice?
Quantum simulations of Alice.
But they don't have her quantum state because you can't clone that.
You're not cloning her state. What you're doing is you're sort of simulating every quantum state she could possibly have.
So by accident.
So by accident, yeah. You can clone a quantum state if you just make every possible quantum state, and you don't know which is her, but that's fine. Yeah.
So the question, what does she see? If what she sees is a thermal bath, then the question, what does she see, means to describe this thermal bath with statistical mechanics macroscopically, or if she can figure out exactly the wave functions of every particle. In this case, it wouldn't be statistical mechanics. You know?
So the classic formulation of the firewall paradox just asks whether she sees smooth space-time or whether she sees what's called a firewall. It's just some other thing that she could see. And my answer is that she sees absolutely everything, because there's now exponentially many Alices, and each one of those sees different things.
So she will not see a thermal bath, for example.
That'll be one of the things she sees. Just anything that is possible for Alice's brain to experience, it will experience.
She's everywhere. She knows the position of every particle, let's say, and their momentum, which is not what statistical mechanics assumes.
I don't understand that statement.
Can you tell me what you mean by many virtual Alice in the computation? I thought the computation is just I want to run computation to extract an EBIT.
That's right, but
So why do you therefore say because the computation is large or because the black hole has a lot of entropy, therefore there are many virtual Alices with?
Just in performing a very long computation, there is the risk that you will simulate Alice in your computer. That is in fact that is the semantic meaning of the computation you're doing, is you are simulating every single thing that could possibly be encountered when falling across the black hole. And so if you make Alices, and that is what's required of you, you're required to do an incredibly accurate computation that simulates the entirety of the black hole, therefore simulating every possible thing that Alice could encounter while falling across the horizon of the black hole.
This last part doesn't seem to follow from the first part.
Yeah.
Again.
Okay, I'll take this question and then I'll take further questions about this to the end.
Just a very naive question.
Yes.
You may have jumped it at the beginning, assuming that everybody knows it.
Yeah.
So what was the basic paradox?
I didn't really.
In what she sees.
So that's sort of, you don't. The basic paradox in what she sees is that quantum mechanics tells you one thing and gravity tells you another. Gravity tells you that as Alice falls across the horizon, she's using a smooth region of space-time that extends all the way to the singularity. Quantum mechanics at least appears to suggest that upon crossing the horizon, Alice should see what's called a firewall, which is a very high-energy region of space-time that is...
I thought that's what gravity suggests.
No, when crossing the horizon...
You talk about changing from one frame to another frame, and because of that, all of the photons are blue shifted.
That is not the prediction of gravity.
I don't understand. Okay. What does this have to do with the computation she performs?
In order to... So, right, good. So in order to manifest the quantum mechanical argument that she should see that, what she actually does is she performs a computation on the Hawking radiation that has already been emitted from the black hole. From that Hawking radiation, she isolates a qubit, jumps in and does a Bell experiment as she crosses the horizon. So that's the actual thing. That's the operational way in which she would exhibit the firewall paradox.
With a different result.
Correct, in gravity from quantum mechanics. Okay, I'm going to close down. Sorry, I know there's some questions.
This is a question I think you like.
I'm not closing down the questions because I don't like them. I'm closing down the questions because
I don't necessarily understand how this necessarily solves anything, because what if Alice was just like 2 qubits and she's falling into a 3 Planck massive black hole?
Well, then you have no reason to expect the classical gravity result to be accurate. You only have a right to expect the classical gravity result to be accurate.
What does she see?
You can, but there's no paradox in that case, because the paradox is the tension between the quantum mechanical answer and the gravity answer. But in the small black hole case you are arguing for, there's no reason to think that the gravity answer is going to be accurate.
Space-time's nuts.
So what is the paradox? What is the paradox trying to resolve here?
The paradox is trying to resolve the question in the limit in which the paradox is actually usually formulated, which is for large semi-classical black holes. Okay, now I'm going to do the second thing, which is also about complexity in black holes, and is somewhat more respectable than the argument I just presented. And it's a question about about how computational complexity relates to black holes. Black holes are in fact going to be the example I'm going to use, but I want you to think expansively. This is really a conjecture that some collaborators and I made about how computational complexity can be understood as being related to the emergence of space-time. Okay, so here goes. First of all, so the computational complexity here, I'm going to mean quantum computational complexity, and in fact I'm going to be more precise about exactly what kind of quantum computational complexity I'm talking about. The space-time is going to be the emergence of sort of large semi-classical space-times, and on the face of it, it's extremely surprising that there might conceivably be such a connection, because quantum computational complexity is a very fine-grained quantum question, and on the other hand, the space-times I'm considering are going to be sort of large, very classical space-times like black holes, large black holes. But there's actually an excellent precedent for the idea that there might be some connection between very quantum non-gravitational things and very classical gravitational things, and this goes back to what's really the best idea in theoretical physics of my lifetime, which is the ADS-TFT proposal of Maldacena from 1997. And what he proved in physics language, or conjectured in maths language, is that there is a duality between a theory of quantum gravity. In fact, it's a string theory. The fact that it's a string theory is not going to be relevant for what I'm saying, but a theory of quantum gravity that lives in n+1 dimensions, and a non-gravitational theory, a quantum mechanical theory, but a theory that does not involve gravity, that lives on the boundary of that space-time. A non-gravitational theory in one fewer dimension. So this embodies the holographic principle, that gravity eats dimensions. And it shows you that there is an equivalence between a quantum gravitational theory in some number of dimensions and a non-gravitational but highly quantum theory in one fewer dimension. And it's in the context of ADS-CFT and the holographic principle that this is going to live. I'm going to claim that the space-time volume of some black hole it will turn out to be is computed, or is rather equal to, numerically equal to, the computational complexity of a non-gravitational theory that lives on the boundary of this space-time. Okay, that's the idea. So the space-time, the property of the space-time I'm going to be interested in is going to be a classical property of a gravitational theory. The complexity is going to be a quantum property of a non-gravitational theory in one fewer dimension. Okay, that's the nature of the conjecture. This is, even by the standards of ADS-CFT, a conjecture, which is why I've added a question mark at the end. Okay, and in particular, the property of the space-time I'm going to be interested in is going to be the size of a wormhole that lives behind the horizon of a black hole in ADS. I realize that some of you may not follow the gravitational descriptions I'm about to make. Basically, the only takeaway you're going to require is that there is some gravitational property of black holes that grows linearly with time. That's it. I'm now going to, for those who know about black holes, describe what that is. So this is a Penrose diagram. Time goes up, space goes sideways, and this is in fact the Penrose diagram of a black hole. This region here, this quadrant here, is the outside region of the black hole, where we live. That's the inside quadrant of the black hole, where if you fell inside you would die, but you wouldn't die immediately. You die when you hit the singularity, sometimes later. So this is the singularity here. Since you can't move faster than light, you're confined to move in your forward light cone at 45 degrees, which means that once you cross the horizon of the black hole, you're definitely going to hit the singularity. Okay. So here's a shell falling into the black hole. So this is a 1 + 1 dimensional diagram representing, a 2-dimensional diagram representing a 3 + 1 dimensional space-time. So I've suppressed 2 of the dimensions, which means that every point in this diagram corresponds to a 2-sphere. And if I send the 2-sphere in, some huge 2-sphere that's living out in infinity, and I send it into the black hole, there it goes. So I'm just sending it in on some light, just lasers, sort of configuration of lasers, all of which shoot lasers in. And there they go, they fall into the black hole and go to 0 size. So this is a trace of the size of that shell as a function of time. It starts off really, really big, and it ends up at 0 size when it hits the singularity. There we go again. Okay, but there is another way to extend a line through this idealized black hole, which is in a space-like manner. And if you do that, and then follow through the size of the 2-sphere that results, this is of course moving faster than light. So this is like a line rather than like a trajectory. There's no way you could follow this line, but you could stretch a rope, conceivably, that followed that line. And you get this. You get that the size of the 2-sphere gets smaller and smaller and smaller, and then opens up again on the other side. This is known as a wormhole. This is very surprising to the people who discovered this in the 1950s, but is now quite standard. That the size of the 2-sphere gets smaller and smaller and smaller, and then opens up again on the other side through the wormhole and gets larger and larger and larger again. Okay, now that's what happens when you... So here's the boundary very long way away at r equals infinity over here. And that's what the 2-sphere looks like. There's a symmetry actually that pushes you up on one side and down on the other, so it doesn't matter which you do. But there is something you can do, which is to ask this question not when the time is anchored at 0 on either side, but ask it when you push it up in time on both sides. So you anchor it at non-zero time on both sides. And what you find in that case is that the size of the wormhole grows. The size of the wormhole grows linearly with time. The length of the wormhole is linear in time. Right, so in fact, if you didn't understand anything I just said, the only thing you need to take away from what I said is that there is a property of classical black holes that grows linearly with time. That's it.
Who coined the term wormhole?
I think that was John Wheeler, who also coined the term black hole. Okay, so that grows linearly with time. And then if you believe in ADS-CFT, if you believe the ADS-CFT conjecture, you think that every property of the bulk every state in the bulk has a corresponding state on the boundary, and every property of the bulk has a corresponding property on the boundary. So in other words, this whole classical space-time here, or the state on this classical slice here, is dual to some property of the conformal field theory that lives on the boundary there. Of this conformal field theory is just some quantum state that lives on the boundary. And in fact, we know for this particular case exactly what it is. It's known as the thermophile double state. It's some overall pure state, but it's entangled between the two sides of the black hole, so that if you integrate out either side of the black hole, the other side is a mixed state with in a thermal state, in fact, with the entropy equal to the Bekenstein-Hawking entropy of the black hole. That's the state at one time, that's the state at some other time. And so the question is the following. So the takeaway from what I just said is there is some property of a black hole that is growing linearly with time. We know that the black holes that live in the ADS side of the ADS-CFT conjecture are the same thing, are dual to states on the boundary. And the question is, what is the property of the state on the boundary that is dual to the linear growth of size of the wormhole? And the conjecture that my collaborators and I have made is that the answer to that question is complexity. So that's where complexity is coming in.
In the sense of computational complexity.
In the sense of quantum computational complexity. In fact, in the categorization that we heard in the last talk, it's going to be the total number of gates. Not descriptive complexity, not depth, not width. It's going to be total number of gates in the circuit that makes it.
This is in the field side, right? In the
Correct.
gravity side, does it correspond to something else?
In the gravity side, it's the length of the wormhole, or the size of the wormhole. And the question is, what does the size of the wormhole in the gravity side correspond to on the non-gravitational side, the quantum side, the boundary side, the CFT side? Yeah.
If you know